Okay, so yeah, just regarding the midterm. Okay, so before I tell you anything about the grade distribution, if you're happy with your score, be happy with your score. Okay, it doesn't matter if people scored over you or below you or whatever. All right, you don't have to compare each other. This class is not a competition. I don't grade based on how you do relative to others. So anyway, I want to say that, okay? I know some of you guys like to beat other people, but that's not the point, okay? It's fine. It's fine if other people score higher than you, and it's okay if you score lower than, or if you score higher than other people. That's not the point. And also, if you didn't do that as well as you would have liked, that's also okay. It's just one test. Your life is not the result of test scores, or I don't know. Okay. I know some of you guys are thinking of going to grad school, or some of you have already gotten into grad school, so congratulations to you. And so, I mean, grades do play a role in that. But in the grand scheme of things, nobody's going to care about your grades, okay? Other than just for that moment of applying to grad school or something, okay? Once you start working, I don't think I was not a great student, okay? In grad school I was I barely got through, but whatever, you guys. Anyway, okay. I can tell you more about my life if you want to know. I don't know what you just said, but okay. So anyway, the grade distribution was I was quite pleased. You guys, by and large, most of you scored well. The median was a 93, and I think Q3, the third quartile was like a 97. The first quartile was like an 85, something around there. Okay. And if for some reason you got like a 60 or something and you're feeling bad about yourself now because I've told you how everybody else did, don't feel bad, okay? It's just one thing. I don't even know, what do I have on the syllabus for how much this test was worth? 18%. Is that what I wrote? Okay. 18% for one class. It's okay. It's not the end of the world, all right? Try, I hope next time your next test will go a little bit better. But you can always recover. Yeah, 18%. So we've got another midterm and another final. Or not another, just another midterm and a final, and then homework. So there's a lot of room to make up for lost points. So anyway, that's that. And then students ask if I curve. I never curve, right? Because it's goes against how I personally believe grades should be done. So that's just me. If I wrote a bad test and everybody did really badly, then I might just raise everybody together, but it's not a relative performance thing. Okay, so now we're in week 5. I can't believe it. Okay, week 5. Some of you are graduating in I don't know, a few weeks. Okay. Oh, and then homework 3 has been posted. It's on neural networks. I've tried to give as much guidance as I felt comfortable giving in the thing, but I hope it goes okay. All right. So here we are. We'll just do a quick recap of kind of where where we were. So we first started off talking about multiple linear regression, multiple linear regression, and we framed this as a minimization problem, okay? And I know linear regression is nothing new for you guys, but and even framing it as a minimization problem perhaps is not new to you either. But we did introduce some machine learning concepts like regularization, like cross-validation, and like gradient descent in the context of linear regression. And I hope using a example that's familiar made it reasonably okay to picking up these kind of machine learning concepts. Okay, but anyway, the big picture is that in linear regression, we've got some way to model a predicted value, and then we chose our model parameters, W hat, by figuring out what values will minimize our loss function. Okay, so we've defined our loss function as the mean squared error or the sum of squared errors or whatever it might be, and we pick our W hats so that this thing is minimized. And in fact, we use the exact same approach when we trained a neural network. Okay, with a neural network, the only difference between a neural network and multiple linear regression is that the way our model makes predictions based on inputs and parameters is just a little bit more complex. There's a few, like we've got more parameters and we got like a couple layers in there, and we've got some sigmoid activation functions and whatnot. But at the heart of it, we just have a system to take inputs, estimated parameters to make predictions, okay? Linear regression has that same framework. Neural networks have the same framework, okay? And then we define a loss function, and in both linear regression and neural networks, we said we're using the mean squared error or the sum of squared error, something like that. And then and we trained our model. We estimate our parameters by trying to minimize that loss function, and we used gradient descent, we used calculus, and that's where we've been, okay? And then we introduced all the other stuff, cross-validation and regularization and all that. Today we're going to take a different approach, all right? And rather than minimizing the loss between what our model predicts and what the data actually has, we're going to try to maximize the likelihood of in a generative model. Okay, so now we're going to define a generative model, and we're going to try to maximize the likelihood. Okay. And so in a generative model, so we're going to start off with linear regression, keep it simple once again. Okay. Our generative model looks something like this. We say the value we observed, t sub n, is equal to our parameters w multiplied by our input x. Okay, so for the nth observation, it's w transpose xn. And then we add some value epsilon, which represents random noise. Okay. And you might be looking at this, and you might be wondering, well, that looks exactly the same as what we had before, okay? And there isn't much of a difference. This is what we had before. We said the way our model makes predictions t hat is by doing w transpose times x. And here I'm saying t sub n without the hat is just w transpose xn plus epsilon sub n, okay? So it's exactly what we had before, but we're just adding a little piece right here, a little epsilon sub n. But and so we can write this as the actual value in our data is equal to what our model predicts plus random error. Okay, and what we had before with least squares regression and neural networks and stuff was that we were just trying to minimize the difference between the actual value and the model prediction. Okay. And today, we have the model prediction, but now we add some random error, random noise. And this is the key difference between a generative model and what we had before. What we had before was we had a way to make predictions, and now we're saying the actual values are what we're predicting plus random error, okay? And that random error is defined by a probability function, and so we can create a probabilistic model because the random error follows some kind of probability function, okay? So it looks the same, or it looks very similar, and indeed they are, but it's just the inclusion of a random noise term or a random error term makes all of the difference and makes it a generative model in our case, all right? I guess this is what I just said. So inclusion of random noise makes it a probabilistic model. Our observations can be said to come from some distribution, and we can calculate the likelihood of our data, okay? And so our goal now is that we want to pick our model parameters that will maximize the likelihood of our data, okay? So we say our linear model is this, okay? Our random error, random noise comes, for now, we're going to say comes from a Gaussian or normal distribution with mean 0 and constant variance sigma squared, right? This might not always be the case, but we will start here, okay? We'll start here where we say the random error, the difference between this and the actual value, the random error comes from some normal distribution centered at 0 and some constant variance sigma squared, okay? And so, our mean function, or the way we predict our values, is W transpose X of N. We can combine that, and we can now say our observations, T, the T themselves, come from a normal distribution centered at W transpose X of N with variance sigma squared, okay? So, so I'm just kind of combining this, the normal distribution here, and so so we're just doing this plus this, and we're getting a new normal distribution, okay? And so now that we've got this defined, our observed data coming from some probability distribution, we have a likelihood, and we can talk about trying to maximize that likelihood. I think I've got a picture. So let's say this is just some linear regression data. All right. The picture that what we are trying to fit is this blue line represents kind of our mean function, W transpose X of N, okay, for all sorts of different values of X of N. And at each point, at each location along here, you've got a normal distribution centered at that line. So the values kind of in this area come from a normal distribution centered here. Over here, we've got another normal distribution centered right here, okay? And so our values, we've got likely to have values here, maybe we'll have values higher, lower, whatever. And then over here, again, we've got some normal distribution centered at this point, and we've got values coming around, okay? So this is, and I just drew 3 locations, but you could just imagine the normal distribution, existing everywhere along this line to kind of represent this is where our data is coming from, okay? So there's some imaginary line representing the relationship between X and the mean of T, which is W transpose X of N, and then the observations we get come from a normal distribution that's centered at these different locations. Okay. Is this the first time, or this is not the first time you've seen this? You've seen this diagram before? Okay, so we're good. Okay, so I think this is what I've been saying. All right, so we want to select our model parameters to maximize the likelihood of observing the data we have. So right now, the model parameters are just W in this vector W. Okay, we're going to just treat sigma squared as fixed. You know, in other things we can treat this as some something that needs to be estimated as well. But right now we're going to just treat sigma squared as fixed. Okay. All right. So we'll take a moment to just review maximum likelihood. I think this is covered already in what, 100B? Is that when you guys do maximum likelihood? Okay. And you know, Professor Christo, he does it quite thoroughly. You're gonna get the simple Miles version here. Okay. So here we've got our probability function of observing some value x given some parameter theta. Okay, so so don't get confused that I'm using x here. All right, so you know, a lot of times we'll define our probability functions as you know, PDFs or PMFs of the function x. Okay, and so you know, just this simple example is that let's say I've got some mystery pouch, and inside this pouch I've got marbles. All right, and then we're going to say some of these marbles are red, the rest are blue. Okay. And so this has a Bernoulli distribution, and if I draw one out, okay, if we say there's 10 marbles in the pouch and 3 are red, then every time I draw a marble from the pouch, we've got a probability of 0.3 of getting a red marble, right? And so the Bernoulli looks something like this: theta to the x, 1 minus theta to the 1 minus x. And right now we've got theta is equal to 0.3 because we've got 3 out of 10. So the probability of getting a red marble is 0.3. Probability of getting a blue marble would be 0.7. Okay, that's simple, right? And then if you've got a bunch of observations, okay, you've got a sequence of x sub 1 up through x sub n, then the probability of all of these independent events is just the product of their probabilities, right? So, so if I ask, what's the probability of getting the sequence red, red, and blue, okay? So in that case, we would write the probability that x is equal to 1, 1, 0. Given that theta is 0.3, it's going to be the product of each of these things. So, you know, it's going to be 0.3 times 0.3 times 0.7, and the probability of getting that sequence is 0.063 of getting exactly red, followed by blue. Okay. I should say with replacement, right? Okay, I'll throw that in there. For it to remain Bernoulli, we'd have to do with. Okay. With replacement. Okay, so this is what we got. With replacement, 0.3 times 0.3 times 0.7, right? Okay. So that's probability functions, and now I want to talk about likelihood functions, okay? Probability functions and likelihood functions, they both describe probabilities. And the distinction is a little subtle, but a probability function is a function of the outcome x, okay? We leave the parameter theta fixed, and we change the outcome. So I said, you know, so back here I have, you know, in the pouch, 3 are red, 7 are blue, okay? And we're treating that as a fixed property of the pouch, okay? And based on that, I'm asking something like, what's the probability I get red? What's the probability I get blue? What's the probability I get this sequence, okay? And as far as probability functions go, if it's discrete, if you look at every single possible outcome, they have to add up to 1, right? So if you do, if you have a binomial thing, if you look at every single possible outcome, all of those probabilities have to add up to 1. That's like a requirement of a probability function. Or if you've got a continuous one, then the whole thing has to integrate to 1. That's like a central defining feature of a probability function. Okay? A likelihood function looks almost exactly the same, all right, except the distinction is that in the likelihood function, it's a function of the parameter theta. Theta is the thing we are changing. okay? And we treat the observed data, x, as fixed, okay? So we treat what we observed as fixed, and we're changing the values theta, okay? And so as far as the likelihood function goes, there's no requirement that the likelihood has to add up or integrate to 1, okay? So, you know, we're pretty much dealing with the same function. It's just in one, the outcome is what we modify, and then in the other, the parameter is what we modify, okay? So this time, as far as if we're talking likelihood, okay, so I've got my mystery pouch. This time, we are treating what's the property, the parameter that defines this pouch as an unknown, okay? We don't know how many are red, we don't know how many are blue. So earlier we said we know that it's 30% red, 70% blue. We treated that as a fixed property of the pouch. Now we're saying what's inside this pouch is a mystery, okay? That it's some variable theta, okay? But instead, we're going to say the observed data is that, you know, I drew 3 marbles with replacement, and I got red, red, blue, okay? So that, the observations I have, red, red, blue, that's going to be fixed, okay? So we treat that as fixed, and we want to know what is the likelihood function for our parameter theta, okay? So this part, kind of this probability, the PMF part remains the same. It's just that theta is now an unknown variable, okay? But x is defined as 1, 1, and 0. So when we take the product of that, we're going to get theta squared times 1 minus theta, okay? So our likelihood function of getting red, red, blue is theta squared times 1 minus theta. Okay, and then so when we talk about maximum likelihood estimation, what we're trying to do is we're trying to find the value of theta that maximizes this function, okay? And so, so we want to maximize this, the probability of getting the sequence red, red, blue, because that's what we've got, all right? So the fact that we got this, we're basically saying we're not all that special for getting red, red, blue, okay? Getting red, red, blue, the fact that it happened to us must mean it's got to be, you know, quite a likely thing for it to happen. So in fact, let's try to figure out what properties would maximize this sequence that I got, red, red, and blue, okay? That's what we want to do. And so what is the value of theta that maximizes this? Well, for that, we can do a little bit of calculus. Whoops, this is supposed to be on 2 lines. Okay, but anyway, so dealing with products can be tricky, right? So we've got theta squared, 1 minus theta. And so dealing with the product can be tricky. So what we do is we take the log of that, okay? So the log of theta squared, 1 minus theta, is going to be 2 log theta plus log 1 minus theta, okay? This should be on a second line. So the log of the likelihood is 2 log theta plus log 1 minus theta. And then what we're going to do is we're going to take the derivative, set it equal to 0, and solve for theta, okay? So the derivative of the likelihood, the log likelihood, is going to be the derivative of this thing, okay? And so that, and we're going to set that to 0, so we get 2 over theta plus 1 over 1 minus theta times negative 1. You chain rule, and then 1, whatever, okay? You do the algebra, and you get theta is equal to 2/3, all right? So the value of theta that maximizes this function is going to be 2/3, and that's going to be our maximum likelihood estimate, right? And so we're going to use the same strategy when we do linear regression, okay? So we're saying the data that we've observed, t sub n, comes from some normal distribution which has this mean and variance sigma squared. And all we're going to do is we're going to just basically take our observed data and make a product of it, okay? And so, so we're going to say, you know, the likelihood, and now it's a function of our parameters w, given our observed data, which consists of the vector t and our input matrix x, and we also have a specified sigma square that we just choose arbitrarily right now, and we're going to say the likelihood of all of our data is going to be the product of each of these things, okay, which is defined by a normal distribution here, okay. And so we've got the normal distribution is defined as this thing, okay? And so so now we're gonna basically the x here is t sub n, and the mu is going to be w transpose x sub n, okay? So that's gonna go into there, and then so we're gonna take the difference between what we observed and what we got, okay? And I got tired of typesetting, so this is so you get some handwritten stuff here, okay? So we've got our likelihood function, which we're going to write L, okay? And I wrote, don't mix that up with your loss function. And so we've got the probability of all of our data, given kind of our input matrix X and W is this is going to be the product of all of this, and so it's going to be the product of all of these normal distributions. And again, this is fine as long as we're assuming that our epsilons come from a normal distribution centered at 0 with sigma squared. And so, so our likelihood is going to be the product of basically all of our normal distribution things, right? So 1 over root 2 pi sigma squared, or just 1 over sigma root 2 pi. And we have all of this, okay? And so the value we observed is t sub n minus our mean, w transpose x sub n, and then we square that, right? And so the likelihood is going to be the product of all of these densities for every single observation we have in our data set. Okay, so this is just kind of what we have. And what we want to do is we want to find the values of w, okay, that will maximize, because we're treating everything else in here is a constant, okay? X sub n is fixed, t sub n is fixed, okay? The only thing that can change is w, okay? Sigma squared, sigma is fixed, okay? Everything else is a constant. We want to do is we want to find the value of w, that maximizes this total likelihood expression, all right? So anyway, to make our lives a little bit easier, because what we're going to do is we're going to take the derivative of this, set it equal to 0, and solve for w. Taking the derivative of this massive product is going to be very painful, so we take the log of the whole thing, okay? So the log of that likelihood function is going to turn the product into a sum, and then and we get this, okay? So we get minus 1/2 log 2 pi minus log sigma, okay? That's just the initial fraction in the front, and then over, so that's this part, and then now we're going to take the log of this e to all of this mess, okay? And so that gives me 1 over 2 sigma squared, and everything else kind of remains there. And so if I apply the summation from n equals 1 to n to this, all right, all of this stuff, these are constants, and so log 2 pi is going to just become n times this, right? So we get negative n times log 2 pi, and then log sigma is just negative n log sigma, okay? And then and the summation comes over here. So I've got 1 over 2 pi sigma squared, and the sum of basically this, all right? So now I've got, what is this part right here? What's that? It's like our loss function, right? This is like the sum of squared errors, okay? It's t sub n minus w transpose x sub n. It's like what our actual value is minus what we predicted, right? So when we take the log of this thing, our log likelihood ends up being, some constants, okay, some constants times, some constant multiplied by our sum of squared errors, right? I guess in my final version, I'll write all of this stuff that I'm saying, okay? But it's a negative times this, right? So if I want to maximize the log likelihood, what's the value of W that I'm going to pick? Just intuitively. It's going to be the same thing, the same W that minimizes the sum of squared errors is going to be the same thing that maximizes my likelihood because I've got a negative value multiplied by the sum of squared errors, right? So the same value of W that minimizes the sum of squared errors is going to be the same value that maximizes the log likelihood, because all it is, the log likelihood just ends up being a bunch of constants, okay, plus the negative version of the sum of squared error, right? So we want to maximize this, so we're going to pick this, right? So anyway, we can go through all of the calculus, but we've already done the work here, okay? We've already done the work, and so we know that if we want to maximize this thing, all we have to do is we have to maximize this, which is going to result in maximizing all of that, right? So here, if I take the derivative, taking the derivative of these constants with respect to W, becomes 0, and all of this, taking the square down, and these cancel out, and here we have all of these dimension things, and I guess eventually I'll typeset this, but I figured I can just write this out, and you'll be fine, right? Okay, so anyway, we get this, and we come down to here, and then if I want to set it equal to 0, I add x transpose x w to both sides, and I left out the last step, but we're going to get W, the best fitting W is going to be x transpose x inverse x transpose t, okay? And so it turns out, so this is not very exciting, right? It's like we did all of this work and we end up exactly where we used to be. It turns out that if your random error, okay, and it all comes down to if your random error follows a normal distribution, okay? If you're saying my random error is centered at 0 and follows a normal distribution, your random error is going to basically have this kind of thing. And so the value that maximizes the likelihood, if you've got Gaussian random error, is going to be the same values that minimize the sum of squared errors, okay? And so so that's where we end up, okay? So we end up at the exact same location, but we took two different approaches, okay? One was we were trying to minimize the sum of squared errors directly, and over here we were trying to maximize the likelihood of our data. It just so happens that trying to maximize the likelihood of our data ends up being the same problem of minimizing our sum of squared errors. This thing kind of shows up on its own when we use Gaussian noise, okay? And so when we use the Gaussian noise, that's what we have, all right? Now, you're not always going to have errors that are normally distributed, okay? So for example, if we're talking about test scores, all right? Test scores are not going to be normally distributed, right? Because there's an upper cap of 100 and a lower cap of 0, okay? Or lower limit of 0. And so, you could have some function that says, we predict you're going to get a 95. It can only be off by 5 on one side, and it can be off by up to 95 on the other side, right? So, so things like test scores do not have normally distributed errors. There's a bunch of stuff that don't have Gaussian noise. But in the case of, if you treat it as Gaussian noise, it turns out that the values that maximize your likelihood will be the same values that minimize your sum of squared errors there. Okay, is that good? All right, I'm gonna do this. I've been dreading doing this, but I think I've got to do our final actual physical roll call. All right, there's like so many people.